So, hello everyone. Uh, Welcome to this live session. Uh, you can post your questions and doubts for this course on linear algebra through geometry. If you are connected, if you are on the Zoom meet, you could probably unmute and ask a question. And if you are on YouTube, you are watching it live, you can post your questions on the YouTube uh, comments. Hello, Aman. Good afternoon. And uh, good afternoon to everybody who's here. Hello, Shivranjani. Hi, Kavya. Hello, Suhasan.
Good
Hi, Jay.
afternoon, sir.
Good afternoon to everybody. Yeah. So if there are any questions, we can go ahead. Uh, Otherwise, I will start discussing the assignment uh, answers. Are there any
Sir,
questions? Yeah.
how can we visualize transposing of matrix?
See, it's not a question of transposition of a matrix. See, the visualization is also about, when you say, um, I mean, you have a matrix, first of all. Let us assume you have a matrix. Maybe I'll take an example and show it you. Give me a minute. Okay, say, suppose I have this matrix, which is A, which is given by 1, 3, and let's say 0, 2. This is the matrix that I have. Now, what I can do is, if I want to visualize this, I mean, there's no question of visualizing a matrix. You could probably visualize the effect of this matrix on a vector. But what I would rather do is, if you want to say, I really want to visualize this, the only thing that I can do is, I can probably take this column vector and this column vector, and then I can plot this like how we normally do, and say that, look, I have this, I have my, let's say, x1 axis, I have my x2 axis. So if I mark my x1, x2 axis values on them, then what I do is I'll say, okay, the first vector that I have is 1, 3, which would correspond to this, like 1, 3 would correspond to this vector, right? And the second vector corresponds to 0, 2. 0, 2 is basically along the second axis. So let me call this as the A1 column, and let me call this as A2 column. The second vector is going to look like this. I'm going to take this 0, 2. 0, 2 is basically here on the y-axis. So I'll take this to be the vector 0, 2. Now, if you say I want to look at the transpose of this matrix, how does it work? Like how you visualize this? Yeah, now plot this as a row vector. So I'll take 1, 0 as the row vector, which is going to be like this. 1, 0 is here. So that will be my first vector. And the other vector is going to be 3, 2. 3, 2 is going to be this guy. So I'll take 3, 2 to be this is my 1, 0 vector, and that is my 3, 2 vector, which corresponds to the row vectors. On the other hand, if you look at this, this becomes my column vector. 1, 3 was here, and the other vector was basically 0, 2. So it's basically this. I mean, you have to treat this as two different entities. You have to take A to be a linear transformation, take A transpose to be a linear transformation. Find out what A does to the vector X and find what A transpose does to another vector Y. That's the way you do. So visualizing this like something I really do not like what is it when you ask me visualization for this. Okay, this is the best we can do. Is that okay?
So can we think like we are scaling and rotating by transpose, sir?
Yeah, ultimately every matrix is going to be some kind of, it will do some uneven scaling, some kind of rotation, some kind of reflection. It would only do that. Okay. For example, you just take the effect of this matrix A, which was basically, let's say, 1, 3, and 0, 2. And let me take this vector x, which is basically, let's say, uh, 1, 0. I'll just take this vector and see like what happens. So if I take x is equal to 1, 0, ax would basically be this 1, 3, 0, 2 into 1, 0, which would basically correspond to 1, 3. If you look at A transpose X, figure out what happens to A transpose X, then A transpose X would be basically this 1, A transpose is going to be 1, 0, 3, 2 into X. So I want to do this 1, 0. So this is going to remain 1, 0, right? So what we see is like, uh, it's the most important geometric operations that happens. If you look at it, it's all typically scaling and rotations and reflections. Okay, is that okay?
Yes, sir. Sir, when we applied transpose to A, shouldn't we
Hmm.
apply it to also the X, sir?
No, 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 no. The transpose operation is basically for this. You only said A transpose X. You did not say A transpose X transpose, right? You only said A transpose X. In fact, A transpose X transpose, if you see, let's see what happens. Can we even do this? Let's look at this. A transpose X transpose. A transpose is 1032. X transpose is basically 10 if you were to take it this way. Can we even do this matrix multiplication? This is basically a 2 by 2 matrix. This is a 1 by 2 matrix. This operation is not even defined. Not defined. Okay.
Yes, sir.
Because the condition is A transpose, the number of columns in A transpose and the number of rows in X transpose must be the same. Here you have two columns and there you have one row. This is not possible. However, you could actually do this. You can take X transpose A transpose. If you take X transpose A transpose, this is basically 1, 0. There are two columns in X transpose, and there are two rows here. So you have 1, 0, 3, 2. Now let us see what do we get here. So what is it that we get? We get 1 here, and then the other is 3. Is that correct? X transpose A transpose is basically, this is a 1 by 2, and that is a 2 by 2. So you basically get a single row, two column matrix. So this is going to be 1, 2 or 1, 3. So now what do we see here? X transpose A transpose is the same as, if you look at this, if you look at AX was 1, 3. X transpose A transpose is 1, 3 written in a row form, which is nothing but it also tells us X transpose A transpose is equal to AX the whole transpose, which is basically the transpose of this vector 1, 3, which is this row vector. Is that clear?
Yes, sir.
Yeah. Yeah. So you have, yeah. Any questions? Is that fine? Like, if there are more transpose of this
Sir,
vector 1, 3. Yeah.
sir, why do we very specific about the square matrices, sir?
Why are we, see, one thing is, uh, see, square matrix, these are things which you have actually done before in, let's say, I will give a completely different kind of interpretation than uh, what we normally do. So, see, First thing is, right from your high school, I mean, when people taught you system of linear equations, you would have actually been taught with system of linear equations, two linear equations and two unknowns or two variables, right? Which means the coefficient matrix will now become a square matrix. I mean, it's a 2 by 2 matrix you get, right? The
Yes,
idea behind using this square matrix is there are some nice things that happen here. What is that? Suppose if I want to find out the solution of the square matrix for a system of equations with two unknowns and two variables, I just take a simple case where we have, let's say, a11 x1 plus a12 x2 is equal to b1, and a21 x1 plus a22 x2 is equal to b2. You can very easily see that the solution to this system of equation is x1 is equal to b1 a22 minus b2 a12 divided by a11 a22 minus a21 a12. And similarly, you will see that x2 is given by b2 a11 minus b1 a21 divided by a11 a22 minus a21 a12. Now, what we say is the solution for this system of equation, you can find the values of x1 and x2, which is basically the solution. It exists whenever this denominator is not equal to 0. When the denominator is not equal to 0, you can find out the value of x1 and x2. For whatever values of b1 and b2 you will give, I will be able to get the value of x1 and x2. And this denominator that we see here, which is a11 a22 minus a21 a12, is basically what we call as the determinant of the matrix, determinant of the coefficient matrix. Is that clear? Now, what happens is, now we understand, like if you want to find the solution to a system of linear equations where the number of equations and the number of unknowns are the same, then you can look at the idea of determinant. You can use the idea of determinant and solve the system of equations. And where the determinant for 2 by 2 is defined like this. You can define determinant only for square matrices. Okay, you can define determinant only for square matrices. Determinant is not defined for rectangular matrices. But unfortunately, what happens is problem solving we will do using square matrices because it's easy to understand. But in real life, you always get a lot of rectangular matrices. You either get a tall matrix or a wide matrix. So once you say that this idea of determinant is what we carry over to solve the system of equation, we can always go back and say that for rectangular matrices, these are not defined. So you say if you can do some iterative procedure and then get it, which is even applicable to square matrices and things. So square matrices form a very, very important idea of this entire linear algebra. Okay.
okay, sir. Thank you.
Yeah. Do we have questions? Some more questions? Is there anybody who has questions? Are there any questions that people are posting? So if you look at, I think there were certain typographical errors in the slides that we had made. In fact, I had clarified those things on the forum itself. So, yeah. Do we have more questions? Are there any more questions? So let's quickly look at, if there are no questions, let's quickly look at the solutions to the assignments. So we'll look at solve these assignment questions. So the first assignment, week 1, first question, it says, for a system of equations Ax equal to B, which of the following guarantees at least one solution? So there are 4 options that you have. a non-homogeneous system with three equations and three variables, uh, homogeneous system with more variables than equation, a system where the number of equations, where none of the equations are scalar multiples of the other, a system where the coefficient matrix A is not square. See, first of all, we must understand whenever we talk about a system of equation having a solution, uh, if you look at a non-homogeneous system of linear equations, there is always a problem where the solutions may exist, may not exist. For example, if we just take this, I'll just give you an example here. Let's consider, let's say 2x plus y is equal to 3 and 2x plus y is equal to, let's say, 4. If I take this example, you see the left-hand sides are the same, but the right-hand sides are different. Therefore, there's no chance that you will get a solution for this. So in this case, a non-homogeneous system with three equations and three variables, it could actually be this itself. You take 2x plus y plus z is equal to 3, 2x plus y plus z is equal to 4. These are three different equations in three variables, but this does not have a solution at all. So it is not guaranteed. Whenever you have a non-homogeneous system of linear equations, you are not guaranteed to have a solution. It may have, if it has, it may have one, or it may have infinitely many, but there could always be a possibility where it does not have a solution. So straight away, you can rule out option A, option C, and option D, because these are subject to the availability of that right-hand side B vector, which should actually be giving you, which should allow you to have a solution. So in that case, the correct answer is therefore a homogeneous system with more number of variables, because a homogeneous system, how many ever variables you take, the right-hand side is going to be zero, all zeros. If the right-hand side is zero, then you can make all the unknown values to be zero to get a solution to them, which means the solution is always guaranteed for a homogeneous system of equation, whether it has more variables than equation or less variables than equation or has the same number of variables as equations, whatever be it, you will definitely have a solution. Okay. Of course, it's not about whether you have one or infinitely many, because the question just asks guarantees at least one solution, which means homogeneous system equations are guaranteed to have at least one solution. The second question, it says if two matrices A and B are of size 2 by 2, then AB is equal to BA. See, as far as real numbers are concerned, you can take x into y is equal to y into x. For example, you take 2 into 3, that is equal to 3 into 2. Therefore, commutativity works as far as real numbers are concerned. But the moment you get into the idea of matrices, it is not guaranteed again that the product of two matrices will be equal to the product of the same two matrices, but taken in the other order. It's not necessarily guaranteed. Therefore, the matrix multiplication is not always commutative. So the question that we have here is when A and B are when A and B are upper triangular matrices, when both A and B are diagonal matrices, only if A is equal to B, then both A and B. So what is the answer for this? So the answer is like when they are diagonal matrices, you are guaranteed to have AB is equal to BA, because in the other case, it is definitely not necessary. And only if A is equal to B, again, A is equal to B, it's a 2 by 2 matrix that you have. So the problem is this. So, okay, so you will have your AB will be equal to A squared, and B is also, even that is correct, but it is all, this case will be true when both A and B are diagonal matrices. Okay. maybe you should look at if only if A is equal to B because it's a square matrix. If A is equal to B,
Only if A equal to B is wrong because it works for diagonal matrices as well.
yeah, true. Okay, so the answer is they only when both A and B are diagonal matrices. That makes sense. Yeah. Suhas, you want to add something to it?
No.
Sir, if B is equal to A, then we get A square, right?
Yeah.
A
Just a
square
minute.
will satisfies.
Yes, just a minute. Just a minute. So, Suhas, you can add your points.
Yes. So the one of the options is only if A equals B, and that is not necessarily true. If A equals B, you can have AB equals BA, but since AB both being diagonal matrices also gives you a commutative product, the option when it
Always
says only A equal to B, that's not correct.
So it holds good. When A and B are both diagonal matrices, AB equal to BA always holds good. Is that clear? Maybe there should be a slightly better wording of the question, but it's yeah, that's what it is. Okay, third question. Which of the following best describes the visual representation of a linear equation in three variables? Yeah.
So option C is also correct if given the option C. So that A equal to
Yeah, I just checked. I mean, only if A equal to B, this option is actually correct. But a general case would be when A and B are both diagonal matrices, I will try to get this reevaluated. Okay, I try
yes,
to get that
yes.
reevaluated. Not a problem at all. Okay. Because if the size 2 by 2 is not mentioned, then maybe it could, if you take a rectangular matrix, then AB may work, BA may not even be possible. Okay. But now that this condition is given, I think we have to consider. I just check. Okay. The third one, it says which of the following describes the visual representation of linear equation in three variables. So what are the, okay. So if you look at the option D, basically it's a plane in 2 dimensions that you take. I mean, in 3 dimensions. So that would correspond to an equation in three variables. Okay, so the rest of them are basically in a plane. So it's a straight line. So one of the axis value could go 0. So one of the variables could be 0. So it's equivalent to saying x plus y is equal to 2 something. So this works. The D is the correct answer. Fourth one, which of the following statements best describe an underdetermined system of linear equations? So underdetermined system of linear equations are where you have a number of variables to be more than the number of equations. So that is underdetermined system of equations. So what it says is underdetermined system of equations are either inconsistent or have unique solution. They are inconsistent or always have infinitely many solutions. They always are consistent and have unique solution. They are always consistent, have infinitely many solutions. So if you see, um, for an underdetermined system where we have fewer number of equations than the variables, uh, so what happens is, let's take this. Let's look at this. Let's take this example itself. 2x plus y plus z is equal to 3. And you have, let's say, 3x plus 2y plus z is equal to 4. Now, what you see is, if you look at this system of two linear equations with three variables, is my screen visible to you? No, I guess. Just a
No,
minute.
sir.
Yeah, I just share my screen. Just give me a minute. Yeah. I guess the screen is visible now, right?
Yes, sir.
Yeah, but I think it's not moving. Are you able to? Okay. Okay, fine. So we have this. When you look at this system of equations where you have two equations and three variables, there is always one free variable which will remain. one free variable. Okay. Whenever there is a free variable, you can have only one of these two. Say, suppose if okay, this free variable ensures there are infinitely many solutions because this free variable can take values on its own. It can take any arbitrary value. So this ensures infinitely many solutions. However, let's look at this. So suppose I have a different set of equations where I have it as to be 2x plus y plus z is equal to 3. And then I take 2x plus y plus z is equal to 4. This is also system of two linear equations with three variables. But the only thing is in this case, you will not have a solution because if you try to solve this, how much ever, whatever you try to do, this 3, 4 will, because if you look at this, I can write this as, okay, you probably wouldn't have started with the linear combination of vectors maybe. If you look at the coefficient of x, it is 2, 2. Coefficient of y is 1, 1. And the coefficient of z in this case is like 1, 1. If you look at the ratio of this, everything is 1, whereas 4 and 3 ratio, if you see, this is not going to work. So it will not have solution. So this would correspond to no solution. So an underdetermined system either has no solution or it has infinitely many solutions. Is that okay? Then a homogeneous system of solution Ax equal to 0 has non-trivial solution if the number of equations equal the number of unknowns, the matrix A is square, the matrix A is all 0, and the system is inconsistent. See, Ax equal to 0, there's no question of inconsistency there. So the last option is ruled out. It cannot be inconsistent because it will always have the solution x equal to 0. So system inconsistency or consistency will not even matter here. Then when you take the matrix A is square, whenever the matrix A is square, suppose if the determinant of that matrix is not equal to 0, you will have trivial solution only. If the determinant is not 0, then x equal to 0 will be the only solution. And then the matrix is, then the number of equations, this has got no relevance at all. Number of equations equals the number of unknowns. We really do not know. But if the matrix A has all zeros, say for example, let's take this. There is no equation at all. There's no system of equations at all. Assume that I have this matrix, which is 0x plus 0y is equal to 0, 0x plus 0y is equal to 0, in which case what happens? You're going to have the 0 matrix to be the coefficient matrix into xy. And if that is going to be 0, 0, then you can put any number of anything here. Other than 0, you can put anything. Therefore, this will have a non-trivial solution. Is this clear? Therefore, this has non-trivial solution. And this non-trivial solution, that's a thing that is being asked for. So when the matrix A is all 0. Okay. Question number 6, it says given A and B, which of the following operations is permitted? I just told you in the first question, we said you have the number of columns of A must be equal to the number of rows in B. In this case, AB is not defined because A has 3 columns and B has 2 rows, not possible. AB transpose is again not possible because B transpose will have 1 row, 2 columns. And then we have A is already 1 row, 3 columns. So it is 1 by 3 multiplying 1 by 2 cannot happen. So AB transpose is not possible. BA transpose is also not possible because B is 1 by 2. A transpose will be 3 by 1 matrix. So that's also not possible. Then B transpose A. B transpose A is also not possible because B transpose is, it's become a row matrix with the 2 columns and 1 row. And A is already a row matrix, so you can't do it. So the only operation that is allowed is B into A because B has 1 column two rows, and A has one row, you have three columns, right? So you can do BA. BA is allowed, so BA will be this matrix. So uh, BA is basically 1, 2, and A is 1, 2, 3. So this is a 2 by 1 matrix. This is a 1 by 3 matrix. So you'll get a 2 by 3 matrix. The product is a 2 by 3 matrix. It is going to be 1, 2, 3, 2, 4, 6. So this product alone is defined. Is that clear? Is this fine with everybody?
Yes, sir.
Let's go to question 7. What does it mean if two equations in a system are visually the same line on a graph? If two equations in a system are visually the same line in the graph, so the first one, it says there is no solution for the system. Absolutely wrong, because they are overlapping. Overlapping means infinitely many solutions. So the first option is wrong. The second option, it says they form a homogeneous system of equation. That is not guaranteed, because it just says there are two lines which are overlapping with each other. If those two lines pass through the origin, then you say it is a homogeneous system of equation. It does not happen. So that is wrong. Then they form a square matrix. That also we do not know. So that is wrong. The correct option is basically they are consistent and dependent. They are consistent because every point on the first line is equal to is always there on the second line. Therefore, the solution to the system of equations is infinitely many. So the answer is it is consistent. And because they are overlapping, they are dependent. Then question number 8, if a matrix has dimension 2 by 3, it can be multiplied with which are the following matrices. So you are you going to multiply it with a 3 by 3 matrix or a 3 by 2 matrix? See, there are two things here. You have a matrix which can be, okay, let's take this. I think the wording should have been a bit better here. The matrix A is 2 by 3. This is a 2 by 3 matrix. Now, I can multiply a B, which could be any matrix by 2, or I could multiply any matrix C, which is basically 3 by, let's say, some K. Is that clear? So, since it is not mentioned whether it is, okay, it's from the right, it is given. The options are from the right, it is given. So from the right means you have to, so the only option that's possible is 3 by 2. This is clear. So, from the right, 3 by 2 matrix. Right? Yeah. So any 3 by K can multiply. So the option is 3 by 2. You can't multiply 3 by 3 from left, because left would require the columns to be 2. That's not possible. Right would require rows to be 3. So there's only one option there, which is a 3 by 2 matrix from the right. So that is possible. That's the only answer that you have. Then we had this question. I think Biswas, are you there?
Yes, sir.
Yeah, we had a nice discussion on the forum, I guess. Let AX equal. Is that correct, Biswas? Hello?
Sorry, sir. Yeah, I was on mute. Sorry.
No problem. You are the one who asked this question, no?
Yes, sir. Yeah.
So I think the understanding here was, okay, when it says all entries other than the diagonal elements are 0, it clearly says, I mean, all the other entries other than diagonal elements being 0, it clearly says the diagonal elements are not 0. But if you want to take it the way that you have told, where you say, no, nothing is said about diagonal elements, so it can be 0. It need not be 0. That's why I also replied to you, fine. If I were to be a professor trying to nitpick your answer, I will give you 0. So I think I will still give it to you, as I said. It says all the entries other than diagonal elements of 0, which means it will have a solution which is bi by aii, considering that the diagonal elements are all non-zero. Otherwise, this will not even work. Okay, Biswas. And the last question is basically it says the solution set of homogeneous system of equations is always empty, never contains a zero vector, always contains at least one solution, does not pass through the origin. See, the question it says is the solution set of the homogeneous system of equations is always empty is wrong because zero vector is already there. It can never contain the zero vector is wrong because it must have the zero vector because zero is a solution to the homogeneous system of equation. So it always contains at least one solution. But when you say the solution system does not pass through the origin, that has to be thought again.
Passes through the origin.
It always, oh, it says does not pass through the origin. So it always passes through the origin. So the correct answer is always contains at least one solution. Is that okay?
It's a zero solution.
Is that fine with everybody? Can we go to the second assignment? If there is anyone who has any questions, can you please post the questions? Are there any questions on the chat or anything? It simply shows that then the are the lectures going fine the way the questions are not being asked? Do I assume that you guys are able to follow the lecture, at least the ones who are representing the class now? Hello?
Yes, sir. Yeah.
So can I safely assume?
Yes, sir. I think. Yeah.
Okay. Okay. Is zero equal to zero even a system? That's a very good question. Zero equal to zero. See, the next question that you'll ask me is 0x1 plus 0x2 equal to 3 even a system? Because there's no variable at all. It is actually a valid system.
As a system, it's a trivial system.
It's a very valid system and it is, I mean, it is there. Okay. It's a valid system. It's just that it is a trivial one. Okay.
Okay, sir. Yeah. Got
Yeah.
it.
Okay.
Yeah.
Yeah. Can we go to the second assignment?
Yes, sir. Yeah.
Yeah. So please. Yeah. Yeah.
Hello. Actually,
Yeah.
sir, pardon.
Go
Sir,
ahead,
I have
Satyendra.
hello. Sir, I have the confusion for like overdetermined and underdetermined equations. That how
Mhm.
we can come to know that it has infinite many solution or no solution for overdetermined and
Ah,
underdetermined.
fantastic question. Overdetermined and underdetermined. There is a way to check whether there is a solution to the system of equation or not. I
Yes,
have
sir.
done that towards the end of this the series of lecture. You will find it somewhere in maybe beyond lecture 40 or something. It is done. Okay. You
Okay.
just need
Thank you.
to look at it. I have done this. Okay.
Oh,
We are,
it has been already done in the week 2 or week
no, no,
1.
no, 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 no. It comes at the later stage where
Okay,
I have
okay,
done consistency conditions. What is
okay.
it to say a system is consistent? When it is
Mm-hmm.
consistent, how do you get the solution? How do you
Okay,
know
sir.
that you will get a solution? So whether
Uh,
one minute, whether you have a solution for a system of equation, one or infinitely many or none, it depends on
mhm.
what is there on the right hand side. For example, you look at this equation that I have 2x plus y is equal to 3 and 2x plus y is equal to 4, this set of equations, this does not have a solution at all. Is that correct?
Yes, sir. This is
This
the
does not
parallel
have a
lines. Yeah, this way we
exactly.
can, by looking, we can come to know.
Exactly. Now, if I change this 3 to 4, let us say I will change this 3 instead of 4, let me change this to 3. Now, do we have solution?
Infinitely
You
many
have
solutions.
infinitely. So, what is it that allowed you to say that it had infinitely many solutions? The value that is there on the right hand side. Is this correct?
Yes, sir.
The ax equal to b. The b tells you that there is a solution or not. The system is consistent or not. Okay.
Okay, sir.
This idea of consistency and existence of solution, I have discussed it in probably week 8 or probably week 7 of our lecture series. Okay. As we
Okay,
go
sir.
there, you will be able to get this. If I do it now, I have to do,
Oh, yeah, yeah, sir.
the.
I'm understanding. Actually, I thought it has been covered because it was in the week 2 or week 1 assignment
No,
you
no,
have
no.
explained, I think.
No. So we,
in today,
yeah, then we have done about consistent. We have just said if it is consistent, you will have solution. Unique or infinitely many. We have never dealt with how to get that. How do you say this is consistent or not? We have not done that. We say if this
Okay.
happens, then you get this.
Okay, sir.
So how
Thank
do
you,
you
sir.
know whether it is consistent or not? It is there at a later week. Okay. I have done this. It is
Okay.
there. The record is there. Recording is there. Okay.
Okay. Okay, sir.
Yeah.
Thank you, sir.
No problem. No problem. Yeah. Assignment 2. So, any other question, or shall we go to assignment 2? Shall we go to assignment 2?
Yes, sir.
Okay, great. Let me pull out assignment 2. V2. Okay. V2 assignment 2. This is here. Just a minute. I'm looking at the questions. Okay. V2 assignment 2. The first question, it says, in Gauss elimination, which of the following is not allowed during the process of row reduction? So the operations are swapping rows, adding a multiple of one row to the other, element-wise multiplication of two rows, multiplying a row by a non-zero scalar. See, swapping two rows is a valid elementary row operation. Adding a multiple of one row to the other, R1 plus K times R2 is equal to R1, valid operation. And multiplying a row by a scalar is also allowed. But element-wise multiplication is a problem because you can't do that. That is not allowed. So that is the correct answer. It says not allowed. So option 3 is correct. Element-wise multiplication of two rows. Then which of the following conditions are necessary and sufficient for a matrix to be in row reduced echelon form? This also, I think this was you were the one to raise a question here, or was it somebody else? In the forum, you
No,
had.
sir, somebody else raised that, and you have
So
answered.
I've answered it there, so I can't blame you for everything. The same, so I'm not doing that. Okay. I think it
Okay, sir.
was Niranjan who raised this issue. He says, which of the following conditions are necessary and sufficient for a matrix to be in row reduced echelon form? Every row contains a leading one and the entries below each leading one are zero. This seems to be a very close answer, except that it does not talk about the presence of zero rows. Where do they sit? That is not there. The second one, it says leading ones move strictly to the right as you go down the rows, and all zero rows appear at the bottom. This is almost perfect answer, except that it says below the leading ones, every element should be zero. So that is not correct. Each leading non-zero entry is one and is the only non-zero entry in its row. If this happens, then there is a problem because you can have the first row with the leading one to be in the third column, and the second row can have leading one to be in the first column, which means that is not the zero to swap. The fourth one is almost the correct answer. All non-zero rows are above any, rows of all zeros. Each leading one is the only non-zero entry in its column. This is correct. But the only point which is missing here is the ones move strictly to the right as you go down there. That is not there. So no answer is correct according to what we have done, because let me see if I can reevaluate this. Okay, this question alone, we will try to reevaluate, or we'll try to skip this question and compensate this question with one additional question in future assignment. Okay, because every option is very close, and it misses that one element. And the last question option also has missed that one element. Okay, so we will try to either avoid giving marks to this question, or we'll delete this question if it's possible. Okay. The inverse of a square matrix A exists only if A is symmetric. The zero matrix is a symmetric matrix, so inverse does not exist there, so that's not there. All the diagonal entries of A are non-zero. Oh, that's fantastic. We can have all the diagonal entries to be non-zero, and we can take this example. Let's take this example where the matrix is this. The condition it says is the diagonal entries as non-zero. So what if I had something like this? Here the determinant is 0. Therefore, it's not a wrong, it's not the correct option. A is in row reduced echelon form. That doesn't even matter. Okay. So the only answer is the determinant of A is non-zero. So that's the option. Then the fourth question, to find the inverse of a matrix using row operations, we multiply each row by -1. We form an augmented matrix A0 and reduce it to IA inverse. Form an augmented matrix AI and reduce it to IA inverse. Apply Cramer's rule directly. See, the first one, multiplying each row by -1 does not even make sense. It doesn't really make any sense. If you augment the right-hand side matrix with 0, it is not going to give you anything. The reason, I'll come to it. Apply Cramer's rule directly also does not make sense. You form an augmented matrix AI and then row reduce it to IA inverse. The reason is this. I wanted to solve this system of equations where the system itself is looking like this. I have a matrix A, and then what I have is, I have, let's say I take A matrix to be a 3 by 3 matrix, or let me take A to be a 2 by 2 matrix. Big deal. I'll take A 2 by 2 matrix, right? And what I'll do is I will take X also to be a 2 by 2 matrix. Till now, what we have done is we have taken X to be a 2 by 1 matrix if I were to multiply on the right with A. So I'll take X to be a 2 by 2 matrix. Now what I'll get is I will get another matrix which is B, which is also a 2 by 2 matrix. This is what I'll get, right? So I'll get X2 by 2 and B2 by 2. Now what it says is, I want to have this matrix A. What does it say? I want to find out the inverse of the matrix. So I do not know what is the inverse. So I'll just retain this. But all I know is, I know that A into A inverse is going to give me the identity matrix, which is 2 by 2. This is the system of equations that I'm trying to solve now. So what I'll do, I will augment this matrix A with the identity matrix, and then I try to do the row reduced echelon form for this. So what I'll get, I will go on till I get I and A inverse. This is okay. So I'll move from AI to IA inverse. So that is the correct answer here. Is that clear? Any questions here?
Sir, I have one doubt.
Yeah, please.
Yeah. This example is fine, but as the question says that we are performing row operations, so shouldn't we be multiplying x from the left hand side instead of the right hand side, because it represents column operation only when you are writing?
That is true, but when you take a matrix A inverse, A inverse, A inverse or A inverse A would be I, unless you very clearly say that left inverse or right inverse. Is that clear? Suhas.
Yeah, right. Okay. I thought the question aligns better with like multiplying x from the left hand side. That's why this problem.
I just have one small point to add over here. So what you're trying to do here is, when you're trying to convert your matrix A to the identity matrix, which happens to be the row reduced echelon form, you're actually performing some row operations, right? You're performing some transformations on the matrix to take it to the identity matrix. So basically, whatever transformations you apply on the matrix A, if you apply the same transformations to the identity matrix, it takes you to the inverse of the matrix. Because you can think about these linear transformation or transformation of rows and columns as multiplying your original matrix by another matrix. So when you multiply A into X equals the identity matrix, it means you're essentially trying to compute the inverse of the matrix A, and whatever row operations you do on the matrix A is being applied to the identity matrix as well. So the transformations that you do to A to take it to the identity matrix are the same transforms that take the identity matrix to A inverse. And that is why you augment the matrix with the identity to compute the inverse and consequently solve the system of equations.
Hello, Biswas. I hope that was fine. Yeah?
Yes. I got Suhas's point.
Yeah. Okay, so let's go to the next question. The determinant of a matrix changes sign when a row is multiplied by a scalar, when two rows are swapped, a row is added to another row, and the matrix is transposed. So when you swap two rows, naturally the sign of the determinant will change. I mean, you check that. Like you take the matrix 2, 1, 1, 2, and swap the rows to 1, 2, 2, 1, you would see that the matrix determinant changes from 3 to -3. Is that clear? So row swapping will result in changing of the sign of the determinant. Sixth question, what is the determinant of a triangular matrix? The product of its diagonal entries, it's always 1. The sum of the diagonal entries, always 0 unless it is the diagonal matrix as such. Okay. So there is another issue here. I think I will have to give this. It says a triangular matrix, but it does not tell me whether it is a lower triangular matrix or upper triangular matrix. It's a product of diagonal entries is correct, because when you take a lower triangular matrix, the diagonal elements will be 1. It will always be 1 in a lower triangular matrix. You will capture it that way, and then you do it. So I think, okay, we'll give it to this. We'll say that the product of the diagonal entries is always the diagonal matrix, the triangular matrix determinant. Okay.
Or also
It's equal to 1. Just check that. We'll check that one. Yeah. Okay. So the next one is Kramer's rule can be applied only when. When can Kramer's rule be applied? When the coefficient matrix is invertible, because you're taking the determinant, right? It is the ratio of two determinants. So the Kramer's rule is applicable only when the coefficient matrix is invertible. Okay. Question number 8, for the system of equations Ax equal to B. Okay, so this the previous question that we did, determinant of triangular matrix, the product of the diagonal entries, that is actually correct. So we'll take it because it's a general answer. Because if you take lower triangular matrix, it's always 1. So it's the same, but a generic case will be the product of its diagonal entries. So that is fine. So
Sir,
for
I
a
have one
system,
doubt.
yeah.
So actually, correct me if I'm wrong. So I thought in lower triangular matrices, all the like upper entries from the diagonal entries, they must be 0. But is there a restriction that the diagonal entries must be 1?
See, typically when you take it as A is equal to LU, when you do a LU decomposition, they typically put that L matrix diagonal elements to be 1 and then capture that pivots in terms of A in the upper triangular matrix. Is that clear? So that is what.
Right. But sorry.
Yeah, go ahead, please.
But so when we divide that when we factorize A into LU, that L in its diagonal entries, that is 1. That I agree. But that is that is one particular example of lower triangular matrix. But if you look at the definition of lower triangular matrix, it says that Aij will be 0 when I is less than j or something like that.
Yes. So what you say is right. So the answer is the product of the diagonal entries. That's the correct answer. Okay.
Yes, sir.
Yeah. I was looking at it from A is equal to LU. Okay.
Oh, okay. Got you, sir.
Yeah. So for a system, Biswas, where are you from, Biswas? Which university are you studying?
Sir, actually, I have done my undergrad from Ramakrishna Mission.
Okay.
Narendra.
Very nice. What are Okay. Okay. So shall we go to the next question, Biswas?
Sorry, sir. Your voice got broken in between. I couldn't hear that. Can you repeat?
No. Shall we go to the next question? It says, for a system of equations Ax equal to B, Ax equal to B in Kramer's rule, let Ai be the matrix obtained by replacing the ith column of A with B. Then the ith value of the solution vector X is given by Xi is equal to the determinant of this matrix Ai divided by the determinant of A. That's the straightforward answer. You don't really have to worry about it. All other things are wrong. If the row reduced echelon form of a 3 by 3 matrix is the identity matrix, which of the following must be true? The matrix is singular, it has no inverse, the matrix is zero equivalent to the identity matrix, the determinant of the matrix is 1. The last one is correct because if it is a singular matrix, you will not get into identity because inverse is there. The matrix has no inverse is wrong because you have got into identity matrix, therefore you will be able to find the inverse. The determinant of the matrix is one. We really do not know what the determinant of matrix is. However, the matrix is row equivalent to the identity matrix. That's what is correct because it is already given here. The question says the row reduced echelon form of the matrix is identity matrix, which means the row equivalent matrix. The matrix is equal to the row identity matrix, the row equivalent identity matrix. Okay. Then consider the system of equations. You have this after performing one step of Gaussian elimination to eliminate the first variable x. What will be the coefficient of y in the second row? This requires some working. So you multiply the first equation by 2, and then subtract the first equation from the second. So you get 4x, 2x, 2x will get cancelled. So this is going to be 3y minus 4y. So the answer is -1. Okay. So you are eliminating, to eliminate the x variable from the second equation, you just need to multiply the first equation by 2 and then subtract the first equation from the second. So this is going to be 3 minus 4, which is -1. Then question number 11, it says let A be equal to this. What is the determinant of A? You can very clearly see product of diagonal elements. It's a triangular matrix, so you have product of diagonal, which is 5. Then suppose A is 1, 2, 3, 4. Which of the following is the 1, 1 entry of A inverse? A inverse is basically adjoint of A divided by determinant of A. Adjoint of A is the diagonal element swapped and the off diagonal element sign changed. So the answer is 4. Oh, what is that?
4 by -2, which is -2.
4 by -2. The determinant is -2. So 4 by -2, which is basically -2. That's correct because A inverse it is also, it's not about adjoint. It is A inverse. So it is going to be 4 divided by -2, which is -2. Then for the following, for what value of A or alpha, A will the matrix 1, 2, A4 have rank less than 2? See, the second column, it is basically 2, 4. So if you want to have the rank to be less than 2, then the second element of the second column must be, the second row must be in the same ratio as the ratio of the first row 2 columns. So here if you say 1, 2 in the first row, the second row must be 2, 4. That will make you get a rank 1 matrix. So that is the answer. So the answer is 2. Then which of the following is the valid row reduced echelon form of matrix A? I think your question number 2 and this are related. It's the same thing. So wherever you find the leading ones towards the right in subsequent rows, and then below which you'll have 0 rows, that will be the thing. So here the option is 1 0 0 0 0 1 0 4 0 4 0. So basically option 1 is correct. Then consider the augmented matrix here. After applying Gauss-Jordan elimination to reduce this matrix to row reduced echelon form, what is the value of third row, third column? So
After 2 steps.
So you have to do 2 more steps of this, and then you will end up getting the answer to be 0. Okay. Which is this value in the third row, third column. So you'll get 0. Okay. So that is about assignment 2. Assignment 3 is due now, or is it done?
I think it is due sometime.
Assignment 3, let me just check.
I think today is the last day.
Still not today's last day.
Today, so I will not discuss assignment 3 now. We still have time, so I'll not discuss assignment 3 now. Okay. If there are any other questions, we can take because I have another session at 3:45. So if you have any other question, I'm ready to take the questions. Or you have any comments about the way the course is done? You want something to be clarified? We'll take that up also. Yeah.
Sir, excuse me, sir.
Please go ahead.
Sir, if the matrix is given like So if you are augmenting the matrix with the equations, like equation is given and we have formed the augmented matrix. Now, how will come to know that we don't have to proceed further to get the A inverse, because it is not necessary that we'll get the A inverse by augmenting. Like if you are doing the operations, so it is not necessary that we'll get the A inverse. So how we can come to know that we don't have to do that part further?
See, when you do elementary row operations on the square matrix A, you must continue to do it till you get the identity matrix. The moment you get identity matrix along A, the identity matrix will now change to A inverse. So you should go till you get the identity matrix from A. Is that clear? Row reduced.
No. I want to say that it is not necessary that, because if A inverse doesn't exist, so
Of
I
course.
think that side A,
No.
we are not going to get a identity matrix on the one side.
Exactly what I'm saying. If you want to find the A inverse, then you must go from A to identity matrix. Is that clear?
Okay.
Are you getting it?
Okay. From
If it
left side
does
we have
not
to.
have an inverse, yeah, if it does not have an inverse, you will see that one of the moment you do the row reduced rational form, when you try to do, you will hit a row of zero. The moment you hit a row of zero, you know that inverse does not exist. Is that clear?
Okay, means last row or maybe one of the row will be
One of
completely
the rows
zero.
will become zero, then you can do a swapping. So if one of
Okay.
the rows become completely zero, then it is stopped. Okay.
Okay, sir.
Yeah. Yeah. Any other questions?
Sir, one problem was there. I was doing like assignment 3. So in
Assignment
that,
3. That is.
one question was there, doubt, like
I
there was
cannot answer that, no, Satendra.
Okay,
Because
sir.
it is due today, no. I'll
Okay,
do it
okay.
next time. Yeah. Otherwise, you post a
Actually,
question.
I was not able to write the things on the discussion form because I'm not getting the idea that how to write on the discussion form.
Okay, tell me
to-
which is the question. Tell me which is the question. I will answer it in the forum. I will not answer it now.
Okay.
Okay. Yeah.
That was the 2 lines were given in the parametric form, and it has been asked to find the point of intersection of both.
Okay.
So 4 options are there. So what I was solving, so I was getting ki both are same lines. So all the 3 options were correct according to me. But the option was taking only one, because multiple choice it was not taking that part.
Okay. So I will check and I'll get back to you. Okay.
Okay, sir. Okay,
I'll
sir.
check
Thank you,
and
sir.
get back. Yeah.
Okay.
Sure. Yeah. Any other question? Like, how are you finding the courses, like the lecture as such? Are you able to follow? Is there anything that you think we have missed it there? Like, you have any comments on till now?
Uh, So it is very interesting. Like we are going in the depth. Like so far, we are knowing ki, we have to do the things in this way only. But now, when you have taught, then we have come to know that okay, this is not so that we directly we apply. There is a some like a transformation is going on. That's why it is happening. So
Okay.
maybe sharing or maybe rotation or something things we are doing, or scaling. So it's very interesting. So we are getting the means ki, core of the subject, that actually what is happening. And sir,
Exactly.
one more, I have a doubt. Like from last that also we are having the interactions, but still we are not understanding the dot product concept, sir. That actually
Okay.
what is happening in the dot product part, we are not means satisfied with that. Somewhere it is mentioned it is rule, so it must be something geometrically it is happening something.
But dot
And what?
product geometrically has a meaning because it will boil down to projection somewhere, or it will
Okay.
talk about the similarity. That is also done at a later stage. Okay, when we do projections, we have done this dot product. See, since we are going, you have all the lectures available now. So it's just that you may probably have to go, look at
Okay.
that,
Okay.
because
It will come later on, means.
it is definitely there. It is definitely there. If it is not there,
Okay.
what I'll do is I'll do a recording of that and then I'll put it in the video. I'll probably host it somewhere else and then tell you that this is what it is. Is that
Mhm.
okay?
So, actually, means what I was confused, ki, like if you are taking the dot product of the 2 vectors, so we are taking the transpose of one of the vector
Yes.
and multiplying with the second column vector of the second one.
Yes.
So, what I was thinking is something transformation must be going on that part.
See, dot product transformation is happening, but as such, if you take dot product, it is just an operation, first of all. Is that clear? It is just an operation that you do, but physical meaning will come when you actually look at it from the idea of projections.
Okay.
Is that clear?
Okay.
Yeah.
Actually, I was just thinking कि by doing the transpose, and sir, when we are doing the transpose, so does it have some geometrical meaning? Like if I'm doing the transpose of
Transpose
the
doesn't
matrix,
have a,
so
it
it has
doesn't change the
geometrical
class.
meaning
No,
something.
no. Transpose is an operation again. I don't think you will be able to give anything as see worst case. If I take a see because I can't even call it as reflection or whatever it is. You just retain it as a transpose operation. That's it.
Okay, okay. Like sir, like when we are finding the A inverse in the hello?
Yeah, hello. Are you able to hear me?
Yeah, hello.
Yeah.
Uh,
So
sir,
actually,
uh,
when you say transpose, you
mhm.
generally do a transpose of a matrix. But when we are taking dot products, is generally for vectors, and for vector, uh, a transpose doesn't really change it. It's for a vector. You can think about it this way. It is a way to represent a point in any space. For example, let's say you're in 3D space. So a vector, a three-dimensional vector is a representation of a point in the 3D space, correct?
Yeah, sir.
So whether you represent it as a row or a column, the vector I'm talking about, it doesn't really change anything. So transpose only makes sense for a matrix, and it doesn't really have any meaning in the case of vectors. I hope this is clear.
Okay. Actually, I was thinking like the matrix is nothing else but the vector representation form is only the matrix. This I'm taking into account actually so far.
Satinder,
Yes, sir.
what I'll do is I'll try to I will put this across as a document and share it in the forum because 3:45 I have to take the
Yeah,
live
okay, sir.
session for my
Thank you
other
for the time.
course.
Okay.
Okay,
Thank you, sir.
I'm really sorry I have to cut you short. If it's possible, what I'll do is I will try to conduct another what you call discussion separately. Is that clear? We will put it in the forum that this will be the meeting link. Whoever wants can join. We'll do that. Okay.
Okay, sir. Thank
Right
you, sir.
now, because NPTEL has to set up the logistics for the next
Yes, sir.
meeting.
So thank you,
My,
sir. Thank you, sir.
my sincere apologies for cutting you guys short now for want of time. Okay, we'll catch up
Thank
again. I thank you all for joining and asking some really interesting questions. Thanks a lot, guys. We will soon have another discussion session like this. Okay.
Okay, sir. Thank you, sir. Thank you, sir.
Thanks a lot. Good day, guys. Thanks a lot to all
Good
of
day,
you and
sir.
all the
Good day,
best.
sir.
All the best.
Good day,
Yeah,
sir.
thank you.